In this video, we're going to look at the economics of exhaustible resources. We can define an exhaustible resource as one that is used up when used as an input into production, and at the same time, its undisturbed rate of growth is zero. The intertemporal sum of the services provided by a given stock of an exhaustible resource is finite. Even when you have recycling occurring, there's going to be leakage. So what we're going to do is we're going to assume an initial stock of a resource at T0 given by S0, and that the rate of extraction at time T is given by RT. So RT is the rate of extraction at time T. So the stock at any given time, ST, is given by the initial stock minus the integral from 0 to T of R tau, where tau is just a parameter used in integration. So ST, stock at any time T, is greater than or equal to 0, and the integral from 0 to infinity of the removals, the rate of extraction over that period, dt, from 0 to infinity, has to be less than or equal to the initial stock, and that's by definition. We ignore the fact that the extraction rate could affect future recoverability. For example, in oil wells, quite often the faster that you pump, the less that is available at the end of the life of the well. So we can write S dot over T is equal to minus RT. So the S, the stock, the rate of change in the stock, is simply given by the rate of extraction. And the limit as T approaches to infinity of RT has to be equal to 0. So no extraction occurs when the resource is exhausted. We assume that the price at time T is given by PT, and that the normal rate of return at any given time is given by RT. Now we're going to find that we're going to change that to a fixed R so that the rate of return is the same in every period. Then we find that the Hotelling rule states that the change in the price divided by the price, so the rate of change in price is equal to the rate of return, or if you like, the growth in the value of the stock is equal to R. This is the fundamental principle of exhaustible resources. So the rate of capital gains from holding the resource must equal the rate of return in the rest of the economy. Let me repeat that so that you get this right. The rate of capital gain, so this is your capital gain, G, which is equal to P dot over P, from holding the resource, must equal the rate of return in the rest of the economy. And that's the fundamental principle of exhaustible resources. So RT is the control variable. We can control the rate at which we remove material out of the mine. RT has to be either 0 or something greater than, but it has to be less than the maximum possible rate at which you can extract anything in a given period of time. If the maximum rate of removal is given by plus infinity, then we have what's called an impulse control, which means that we allow for these discontinuous jumps. And as I noted, we tend to let R, the rate of return in the rest of the economy, be equal across time periods. And we assume for convenience that there are no extraction costs. So then the objective is to maximize the present value of the mine or the exhaustible resource from 0 to infinity, and that's given by e to the minus RT. This is the discount factor, the price times the rate of extraction at any given time, and that is the integral over period from 0 to infinity. If the rate of extraction is at its maximum plus infinity, then we simply maximize the term e to minus RT times the price at that time times S0. All right, now we can look at this from the point of view of a little diagram, and we see that if this is the red line is the description of what the price does over time. And then we have these ISO present value lines, which tell us what the maximum of present value is. then we find that this occurs here where there's a tangency point between the price, so the rate of change in the price, and the isopresent value line, and that occurs at t infinity, where we extract all of the resource if this is the situation that we're at that plus infinity, where the maximum rate of extraction is given by plus infinity. So you see that it turns out that the tangency occurs on this line here. We cannot achieve this maximum present value here. We can achieve this one at various points here, 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 but that would be a lesser value of what the present value of the resource is worth. Now, if the rate of extraction is the maximum rate of extraction, that is less than infinity, less than taking all of it at one time, then we construct the Hamiltonian. And the Hamiltonian in this case is given by e to the minus RT, PT RT. So this is that term up above here, this term here. And then we subtract from that lambda t, the Lagrange multiplier or the dynamic multiplier at time t times RT. And we can simplify that a bit by writing e to the minus RT PT minus lambda t, lambda is a function of t, all multiplied by the rate of extraction at a given time. Then we take the conditions that the partial of the Hamiltonian with respect to lambda is equal to s dot. That gives us back the original constraint. The maximum principle states that the partial of the Hamiltonian with respect to the control variable r is equal to 0. And the third equation is that the partial of h with respect to the state variable, s is the state variable, is equal to minus lambda dot, where lambda is the co-state variable and lambda dot is simply then rewriting this is minus the partial of the Hamiltonian with respect to the state variable. So for the above Hamiltonian, we get that s dot is minus r. So the rate of change in the stock is equal to the rate of extraction, the negative of the rate of extraction. The maximum principle, number 2 here, states that the partial of h with respect to r is equal to e to the minus RT times the price at given time minus lambda t equals 0, and lambda dot minus partial of h with respect to s is equal to 0, and that means that we got lambda as a function of t equal to that lambda, which implies that lambda is given by the discounted value of the price, and we'll call that equation number 1. The transversality conditions give, so these are your endpoint conditions. So at the terminal time, the Hamiltonian is equal to 0. That means that if there's any resource left, the cost of extracting it would be greater than what it's worth. So in other words, we leave some resource, we don't exhaust it completely because it isn't worth doing, and we can write that as e to the minus r big T times the price at big T minus lambda and multiplied by the rate of extraction at time t equals 0. And that shows you that either the rate of extraction is 0 or this term here in square brackets has to equal 0. If that's the case, then we get lambda is equal to minus r to the big T, pt, which tells us that either that lambda, the co-state variable, is equal to the discounted value of the price at that point. So now we look at what PT is. So from 1 and 2, from this equation and this, we set the two equal to each other, and we get that the price at any given time is equal to lambda e to the RT equals RT minus big T times P of T, of big T. So the optimal solution is that the rate of extraction in the final period is 0 when the price is less than some value k, and k is given by this expression here, and RT is at the maximum possible rate when in that last period when the price is greater than k. And that gives us a bang-bang extraction or chattering. So here's what that looks like in this diagram here. So this solid line, black line is e to the power r times t minus little t minus big T, so the number of periods before you get to the end point, multiplied by the price, big T, and then this again is the path of the price over time. And we see that we have these intersection points occurring at times of T0, T1, T2, and T3. Remember, these are your final time periods here, and pardon me, they wouldn't be the final time periods. So what we get is we get a bang-bang extraction. So extraction is 0 up until we hit T0. Then it hits its maximum point over this range here. Then it drops to 0 again because this is below, the price is below this expression there. And we note that that's the case here. So we have that 0. Then again, we get maximum extraction, and then it drops again to 0. So this is a bang-bang extraction, or what we call chattering. Now assume costs. We haven't had costs in here, so costs are a function of the extraction rate and time. And we want to maximize now the integral from 0 to infinity of the discounted net revenue in every period. So price times amount extracted minus the cost during those periods. Again, we have this requirement that S dot is equal to minus R. So this is our state variable or state expression, the constraint, the dynamic constraint. ST always has to be greater than or equal to 0, as does the extraction. So then we form the Hamiltonian like we did previously, but now we've got that cost. And this is the expression for this term here. We've simplified it. All right, and it's discounted. Minus lambda RT, R at any given point in time. We can rewrite that simply as the discounted factor here multiplied by P minus lambda e to the RT multiplied by the extraction rate minus the cost. So again, we take the derivatives, and the first one we get is that we get this expression back. All right, so this is our dynamic constraint. And then the partial of H with respect to R equals 0. That's our maximum principle. And that gives us this expression here. The e to the minus RT will cancel out because of the 0 on the right-hand side. And finally, we get that lambda dot is equal to 0, which implies that lambda at any time t is given by a constant lambda. So the partial of the cost function with respect to the extraction rate is the marginal cost of extraction, and that's given by the price minus this expression here, which refers to the future value of the resource. So let's assume that the effect of extraction on cost is greater than 0. So in other words, the more you extract, the higher the cost. And what happens is we can look at different cost functions. So here we have the straight line here is simply the price at any given period of time minus lambda e to the RT. So this is the future value of that resource. And we have two cost functions. One is the red line, which is cost B, and the other one is cost A. And if we take the derivative of cost A, we get this line here, which is tangent to it. So this is your marginal cost at that point. And this line is parallel to this one here. So this becomes the optimum, and we would extract that amount of the resource R star A. This one, R star, that should be a B. R star B, and that's the amount that we'd extract if this was the cost. In other words, we don't extract anything. If price and cost functions oscillate over time, it's the optimal production schedule may alternate between shutdown and production. And that's what we saw up here in these diagrams, where we alternate between production, meaning extraction, and shutdown, meaning no extraction. Since the extraction cost is nonlinear, the optimal production rate now varies continuously rather than switching from 0 to R max by discontinuous jumps. So there's no binding. If we have no binding extraction constraint, we see that this we get these bumps here where this is our optimal extraction rate, and these correspond to what we had before. If the extraction is binding, if there's a binding extraction constraint, then R star will look like this. If this is our maximum possible extraction, then we just follow this path here, and instead of going up here and increasing our extraction rate, we're at the maximum, and then we decline and move over like that. Okay, that's one example of where we use the Hamiltonian function to determine an optimal extraction rate for a natural resource that's exhaustible. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.